The ratio test with endpoints, part 2. In this video, I'm just going to do a couple examples with you, finding radius and interval of convergence of a couple series. Let's look at our first one. The sum from 1 to infinity of negative 1 to the n plus 1 of x plus 4 to the n over n squared times 3 to the n. Our main goal is to find the interval of convergence. We will find the radius in the process. So radius and interval of convergence say, let's do the ratio test, which is the limit as n goes to infinity of the nth plus 1 term divided by the nth term, which of course we flip and multiply, giving us this. I can simplify this down. We would get x plus 4 on top. We would get 3 on the bottom. And the n squared and n plus 1 squared would disappear. This is the ratio, which means my series will converge when my ratio is less than 1, or when x plus 4 is less than 3. Building the number line with my center at negative 4, this says find all x's that are no more than 3 away from my center. So the interval of convergence of the series is definitely negative 7 less than x less than negative 1. But what happens to the endpoints? Because the ratio test fails at the endpoints. I'm going to erase this so I just have a little bit of space to work with down here. Because I want to see my series as we do this. So let's plug in our endpoints. If I plug in x equals negative 7, I'm going to put this back into my series. I get the series, and I'll leave off the limits just for space, of negative 1 to the n plus 1. And then I have negative 7 equals x, which would give me negative 7 plus 4, or negative 3 to the n, over n squared times 3 to the n. And I'm going to simplify this so I can see what's happening. I get negative 1 to the n plus 1 times negative 1 to the n times 3 to the n over n squared times 3 to the n. Putting my negative 1's together, I get negative 1 to the 2n plus 1. All right, when we multiply, we add powers. My 3 to the n's disappear, and I get over n squared. Now, negative 1 to the 2n plus 1 is always negative, but it doesn't really matter. Because if I rewrite it as negative 1 over 1 to the n squared, I have the series, which is a converging p-series. So I know that the series converges at x equals negative 7, so I will add the equal sign there. What about at x equals -1. Plugging in, I get the sum of -1 to the n plus 1. And then I get -1 plus 4, that is 3 to the n, over n squared times 3 to the n. The 3 to the n's cancel. And I am left with, in this case, an alternating series whose positive terms decrease to 0, which means that alternating series converges. And likewise, my original series will converge at the endpoint x equals -1. So the interval of convergence is -7 less than or equal to x less than or equal to -1. One more example. Way back when we were doing power series, we saw that the arctan of x was equal to the sum from 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. And we saw that this was true for x between -1 and 1. That is, my series, plugging in any x between -1 and 1, would exactly equal arctan of x at that x value between -1 and 1. But what about the endpoints? Well, let's take a look at the endpoints. Let's plug in x equals 1 to start. At x equals 1, we get the sum from 0 to infinity of -1 to the n, and then 1 to the 2n plus 1, because we plug in x equals 1, but 120 power is 1, so I don't need to write it, and then over 2n plus 1. Notice that this converges by the alternating series test. So I can do x less than or equal to 1. How about x equals -1? Let's put into our series for arctan. I get the sum from 0 to infinity of -1 to the n times, now I plug in x equals -1, -1 to the 2n plus 1 over 2n plus 1. Looking ahead just a little, if this series alternates, it converges. If the series does not alternate, it will diverge. Cleaning up the -1 to the powers, I get -1 to the n plus 2n plus 1, or -1 to the 3n plus 1, and then over 2n plus 1. So all I'm really checking is to see, does this series alternate or not? If I plug in n equals 0, we get -1 to the 1, which is negative. If I plug in n equals 1, we get -1 to the 4, which is positive. And if I kept going, I would see that the series does indeed alternate, which means it also converges by the alternating series. And so my summation, my polynomial, converges exactly to arctan of x at both of the endpoints if I were to sum all of the terms, that is the infinite number of terms. One follow-up problem that I like to give is the following. I want you to evaluate this. 4 times 1 minus a third plus a fifth minus a seventh plus forever. To do this problem, you have to recognize that I am asking, at least in part, for the arctan of x. Because the arctan of x equals x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7th, etc. And in my problem, all I did was multiply everything by 4 and then plug in 1 for each x. And since I know that the arctan of x converges at x equals 1, I'm really asking for 4 times the arctan of 1, which is 4 times pi over 4, which equals pi. So 4 times 1 minus a third plus a fifth, etc., etc., exactly equals pi.